This video in the probability unit is called Measures of Centre of Discrete Random Distributions. What does that all mean? Well, we're going to deal with three things here. The mean, the mode and the median. You might have heard of the mean before. It's the average value. How does this relate to probability? Well, we talked in previous times about discrete random variables, and we've given them values denoted by capital letters, usually X, Y or Z. And the expected value is, if you conduct a number of trials, and average the results, what's the average result or the expected value over lots of different trials? So the expected value is the average value of the discrete random variable. It's also referred to as the mean of X, or sometimes, more rarely, the expectation. It's denoted by E of X. Okay, that's the notation there, capital E and the capital X in brackets. And it equals the sum of the probabilities multiplied by the X values. I just realised I missed a little X out there. So it's X, the sum of all the X's, the values that the variable can take on, multiplied by all the probabilities. And that's for all X's. Now, it's not going to do necessarily, in fact, it almost always won't assume a discrete value, so it can be a decimal. Okay, even though we're dealing with discrete values of 1, 2, 3, 4, 5, 6, etc., the expected value can be a decimal, 2.7. So that's the important formula there. That one there. Expected value of X, the sum of all the values that the variable can take on, X values multiplied by the probabilities. Let's have a look at a practical example. Find the expected value of a random variable that has the following probability distribution. So this could be a spinner, for example, a biased spinner. We've seen spinners before, they have different sectors. Okay, the sectors might be different sizes, and if they are, there'll be different probabilities for it landing on certain sectors. So that could be something like that. So you've got the value that X can take on, 1, 2, 3, 4 and 5. The probability of 1 is 2 on 5, of 2 is 1 on 10, the probability of 3 is 3 on 10, the probability of 4 is 1 on 10, 5 is 1 on 10. So they're the probabilities. And now we look at our formula. There it is. Let's see how it works in practice. So to find E of X, we multiply each X value in turn by its probability. So 1 times 2 on 5 plus 2 times 1 on 10 plus 3 times 3 on 10 plus 4 times 1 on 10 plus 5 times 1 on 10. Okay, so it's those 4 separate calculations. Notice how we've multiplied each time the X value by the probability along the line. So now it's just a matter to find out that expected value is to calculate this here. Okay, and we'll do that on the next slide. Okay, so if we complete the calculation, 1 times 2 on 5 is 2/5 plus 2 on 10 plus 9 on 10 plus 4 on 10 plus 5 on 10. Now we could replace 2 on 5 there with 4 on 10 quite simply, so they're all over the common denominator of 10, and what we're going to get now is 4 plus 2, 6, 15, 20, 25 on 10. Okay, sorry, miscalculation, it's actually 24 on 10. Fix it up. That of course equals 2 4/10 or 2 2/5. If you wanted to look at a decimal equivalent of that, it would be 2.4. So the expected value is 2 2/5 or 2.4. So if we span the spinner numerous times, and there are our probabilities, and averaged what we got over time, that would be our average value, 2.4. Next question, finding the unknown probability first, and hence determine the expected value of the random variable. Right, this is a pretty similar question to the last one. We've just got one thing here. We've got to find the value of A there. Okay, and if we look at that value of A, we know that for it to be a discrete probability distribution, two things need to happen. Our probabilities need to be positive and between 0 and 1, and they are, and they also need to add up to 1. So if we look at our situation there, A is going to be 1 minus, those two added together is 0.6 plus 0.1, plus 0.1 there is 0.7, plus another 0.1 is 0.8. So if we add those four together there that I'm underlining, they're 0.8. So to find A, it's 1 minus 0.8 equals 0.2. So that's the missing value. So I could actually go back to the table here and replace that now with 0.2. And that gives me the complete table, and it means now I can find the expected value of x. So let's put that complete table here. There it is. And now to find the expected value of x, I'm multiplying my x values by my probabilities. So expected value of x equals 2 times 0.2 plus 4 times 0.4 plus 6 times 0.2 plus 8 times 0.1 plus 10 times 0.1. So once again multiplying all the x values by the probabilities, and if we calculate that, we actually end up getting a nice round value of 5. As I said, it can happen, you can get a discrete value, but expected values are not necessarily discrete values, they can be decimals. So there we go, that's that question done. Next question, find the values of A and B of the following probability distribution if E of x equals 4.29. We're starting to head into questions that could possibly crop up in exams now, rather than the more basic ones. Probably also means that we can use, if we're looking at finding two variables here, that we're going to use simultaneous equations. So how can we weave simultaneous equations into this? Well, the first and most obvious one, if we look along the line here, we know that those 7 values there, on the bottom here, tick them, they're going to add together to equal 1. So let's start on that basis, that that's going to be one of our equations. That 0.1 plus 0.1 plus A plus 0.3 plus 0.2, just running out of room here, and I like to do all in one line, so let's just actually just move this over this way a little bit so that I can fit it all in one line. Plus B plus 0.2. Okay, once again I've gone off here a bit, try and get it all in one line. Might do it down here, I think. Might be the easiest. That's better. We know that all of those are going to equal 1. Not a very straight line there, but you get the idea. Which means, if I add all those up, 0.9 plus A plus B equals 1. Therefore, A plus B equals 1 minus 0.9 is 0.1. So there's the first of my equations here, and it's A plus B equals 0.1. So we'll come back to that one in a minute. Now the other equation we'll work out will involve this bit of information here. So we know the expected value. And we know the expected value, according to our formula, is E of x equals x times the probabilities. So let's look at that down here. So in other words, 1 times 0.1 plus 2 times 0.1 plus 3 times A plus 4 times 0.3 plus 5 times 0.2 plus 6 times B plus 7 times 0.2. All of that, okay, that's the expected value. It's applying that formula. The x values multiplied by the probabilities. All of that is going to equal 4.29. We simplify all that. Excuse me. We get 3 lots of A plus 6 lots of B on the left there, plus 3.9 equals 4.29. Therefore, 3A plus 6B equals 4.9 minus 3.9 is 0.39, and that gives us our second equation just there. There's our two equations, and what we can do now, we'll label them equation 1 and equation 2. There they are. Now, a couple methods here. We can use substitution or elimination. Doesn't really matter. What I might do here is use substitution. So we're going to make A, according from the first equation, 0.1 minus B. So I've taken that first equation there, and I've got A by itself. Therefore, now utilising equation B, therefore, 3 times 0.1 minus B. How did I get that? Well, I've just substituted A there for that. Plus 6B equals 0.39. 0.3 minus 3B plus 6B equals 0.39. Get like terms on each side. Negative 3B plus 6B is 3B on this side. Take the 0.3 over and subtract it from here. We get 0.09. Therefore, we divide through by 3. B equals 0.03. Now we can substitute back in equation 1. So substitute B equals 0.03 in equation 1. So A plus B, which is 0.03, equals 0.1. Okay, and A will equal 0.07. So there's our answer. Okay, B equals 0.03, A equals 0.07. Last question for this video. Nikki and Melanie devise a gambling game based on tossing 3 coins simultaneously, that means at the same time. If 3 heads or tails are obtained, the player wins $20, otherwise the player loses $5. In order to make a profit, they charge each person $2 to play. What is the expected gain to the player? Do Nikki and Melanie make a profit? Is this a fair game? Alright, first of all, let's have a look at the scenario we're looking at here. It's the tossing of 3 coin scenario, which you've seen before, and we can represent it by a simple tree diagram representing the 3 coins in turn. And then we can get ourselves here a bit of what's called a sample space here, which is the outcomes that are possible. Put them in set brackets here, and you can see there's 8 outcomes possible. We've looked at that before. So we've listed all the possible outcomes, and now we can place that information into the table. So X is obviously the number of tails that are thrown. Okay, there's either 0 tails, 1, 2 or 3, and you can see the probabilities there for each of those. 1 in 8 for no tails, which is 3 heads. 3 in 8 for 1 tail, which is that outcome there, that outcome there, and that outcome there. That's 3 out of the 8 outcomes. 3 in 8 chance of 2 tails, which is that one there, that one there, and that one there. And lastly, 1 in 8 chance of getting 3 tails. Now, with these gambling type questions, we actually add in a third column. So I've got here gain in dollars. So we know that we gain $20 if we get the two outside outcomes, that is 0 tails or 3 tails. We lose $5 for anything else. So that's where the number of dollars comes there in the gain part of the table. Haven't factored in the $2. We'll do that. Remember, if we look back to the question, a couple of slides here, we talked about $2 to play. I haven't factored that into the table, and typically we don't. We can do, but I think it's less confusing if we leave it out of the table. We'll factor it in later. So that's the setup of the question. Alright, so the first question we're asked to look at here is what is the expected gain to the player? So we're going to use our usual expected value formula, which is this guy here, the sum of. But instead of using the x values when we're doing these to look at the gain of the player, we're actually going to use these gain values. So you'll see what I mean here. So instead of it being 0 times 1 on 8, we're actually going to use 20 times 1 on 8. Because we're looking here at the expected value of the gain to the player. So it's 20 times 1 on 8 plus neg 5 times 3 on 8 plus neg 5 times 3 on 8 plus 20 times 1 on 8. So you see there, if I change pen colour, you can see how I've multiplied the gains here by the fractions, the probabilities. And we do that typically when we're looking at a gambling type question. We're looking at the gain that the player will get back.
Dad, I'm not done with my tea yet.
Okay, that's right. Apologies for that, my daughter just asked me a question. Okay, back to the calculation here. So we got to this stage here of calculating this. So if we look at going a bit further here, get that calculation. We get 20 on 8 minus 15 on 8 minus another 15 on 8 plus 20 on 8 equals, so that's 40 on 8 minus 30 on 8 is 10 on 8. If we convert that to dollars and cents, that equals $1.25, which is $1.25. So you can do that easy enough on your calculator, just 10 divided by 8, $1.25. So the expected gain is $1.25, but each game has a cost of $2. So the player in fact loses, so minus $2. The player loses, okay, an average of 75 cents per game. Remember, this is averages, expected gain. Okay, it's not what's going to happen each game. So expected gain is $1.25, but because the entry fee is $2, the player loses on average 75 cents per game. And that sort of answers the next question. If we go back to our questions, the next question was, do they make a profit? Okay. Well, yes, they do, because the player is losing 75 cents per game. The girls, this is the answer to question B, the girls make a profit of 75 cents per game. Question C was it a fair game? And no, this is not a fair game, since the cost of the cost to play, sorry, cost to play each game does not equal the expected gain. The expected gain of each game. So what does that mean? Well, if we'd have got here, $2 as the expected gain and $2 to play the game, it will be a fair game. Whenever there's a mismatch between the expected gain here and the cost of the game, in other words, a mismatch between those two values, means it's not a fair game. So it's pretty simple yes or no answer to that question. Okay, I hope that has got you started there with expected value, and next video will be about expectation theorems, but that should enable you to get started with exercise 10C, questions 1 through to 16. Good luck with it. That's it for now.